Okay, I think we're ready to start. That means welcome in the first proper math session in our calculus class. That means I will start with the basic concept of calculus, the definition of calculus, and hopefully I will try to cover section 1.4, 1.5, and I will just touch section 1.6. I will just explain the concept, and the practice problems I will add later, okay? Because I don't think 1 hour is enough, but as I promise, I will keep the session not longer than like 60 minutes. And you can remind me if it will be like about around the 10 o'clock. Okay, that means let's start. I will actually use that screen. Okay, and I think I will switch off the camera. It's just better. Okay, that's the basic concept of calculus. I don't know if you had calculus in high school or if you had any experience with calculus, but what I will do, I will start everything from the scratch. That means let's see what I have. The first important information is that the calculus, like overall, we can call is the mathematics of change. Okay? That means everything what was before calculus, like algebra, geometry, pre-calculus, of course, it's like more static. But calculus is like more dynamic. Okay? From Latin, calculus means like small pebble. I don't know if my pronunciation is good. And they were defined in calculus as a counting, like a calculation. Yeah, and makes sense. Calculus, like calculation. As I said, is dynamic because it's the study of continuous change. Yes, it's the mathematics of change, continuous change. Like the same way, like geometry is the study of shape. Algebra is the study of like a generalization of arithmetic operations. Okay, and what we do have 2 branches of calculus. We have differential calculus and integral calculus. Differential calculus, that's what we will start with. It's like concentrating on the rate of change, the instantaneous rate of change, the rate of change at one moment. And the integral calculus is talking about the accumulation of quantities like the areas under the curve, between the curves, volume. Okay? And we will also have time for the integral calculus in this class. Okay, that's the short introduction. And then I have a few slides about calculus that we can see. In order to reach calculus, we have to be confident with algebra and all of the pre-calculus stuff, and then we will learn the basic concept of calculus, the limit process. Okay? And then calculus will be the output. And I have a few comparisons. We will compare the stuff that we can calculate without calculus and with calculus, and this is the differential calculus. That means, for example, we can find the value of the function, of course, no problem at all, or we can try to find the behavior of the function, how function behaves close to the point, the given point. Not exactly at that point. We can see this is the solid dot, right? Solid dot, and this is, we don't even have, function doesn't even have a value. That means how function behaves really, really close to quantity C on the left and on the right-hand side. That means I think we need calculus. And then slope of the line, no problem. Slope of the curve or slope of the tangent line. That's almost the same thing. We need calculus. And this will be our main application. Average rate of change, the same, no problem. We have distance, we have time, we can definitely compute the average rate of change, speed in this time. But what's happened? How can we calculate the rate of change at one point, exactly at that instant, which we will call instantaneous rate of change? All right, we will think about this. And then a little bit of, we will probably not touch this stuff, or like, let's say this, the height of the curve when the x is exactly c, which it's the same like the value of the function from the previous slide. Or we would like to find the maximum height on the given interval. Yeah, like how can we find out where is the maximum point? I think calculus will help us. And then yes, the area of the nice like the nice shapes with the straight lines, or the area under the curve. Okay, the length of the line segment, no problem. The length of an arc, yeah, that's things. Some of the stuff are from the calculus 3. That means I will not even talk. I mean, you can pause the video, you can check the slides later. Yeah, the surface area or the volume. We will talk about the volume of the cylinders, rectangular solids, or the surface area of the solid of revolution. Right? We will try to use the calculus. And the sum of the finite number of terms, the sum of an infinite number of terms. Probably you can think, we put this, that it's not even like possible to add infinitely many terms, but again, the calculus will help us. But that's calc 2. Okay, that's me now what we have. We do have chapter 1, and the first section that we will focus on, it's 1.4, a tangent line, and the velocity problem. That means, first of all, in this section, we have to find out what tangent line means. Do you think? I know that it's not the real classroom, but I still like to ask the question. Do you think you know what is the tangent line? Like, how can we define? You can type your answer, or you can try. Yeah, we will not share the microphone, I believe, because it's going to be too chaotic, but you can try to type the answer. Okay, I can definitely wait. That's what do you think? What tangent line means? Tangent. Like any description, any definition. Okay, we have one answer from Zach. A ray that intersects the curve at one point. Yes, I think it's close enough. That means, let's see, because actually I really like this answer at the moment. That means, let's see this. The definition that you gave us, it's almost accurate, because just the word, you actually use the same word, intersects, like Euclid, one of the, I'm pronouncing that name probably in the German way. Euclid is one of the famous mathematicians. That means that's how he defined the tangent line, that the line that is intersecting a curve once. And this is correct, but what we find out later, that for more complicated curves is a little bit like not really accurate, like a little bit inadequate, because I can show you an example, but for the circles works perfect. But of course, that's the idea. Like tangent from Latin means touching, right? That means it's like the curve is touching the curve, which the line is touching the curve. And this means that we have one point of the contact, one point of intersection. But we have to be careful with the word intersection, because I have on my, actually I can show you. On my next slide, I have this, I can show you the entire slide. That means let's look at the curve C, and let's look at the blue line L. Do you think this line is a tangent line? It's intersecting once, but yes, of course, no. That means I can definitely see that you know, you have the feelings, like you know what exactly tangent means. Yes, thank you, Zach, thank you, Eric. It's not, it intersecting once, but it's not a tangent, because definitely something is wrong. As I mentioned, tangent from Latin means touching. That means this is not really touching, this is like crossing. Yes, and we don't like this. But what about the line T, the pink line? Do you think this line is a tangent line at the point P? Yes? Thank you, Eric. Yeah. This is definitely tangent line, but what I'm just looking at like a really, really close interval on the left and on the right-hand side at the point P, okay, including point P. That means this is definitely tangent line at the point P. And of course, I am proving that the word intersecting, it's not adequate, because we do have another point I can call point Q. But in calculus, we're not looking like at the whole big picture. We're always trying to minimize, limit, right? I will start to use the word, we will limiting some situations, that we limit it just to this neighborhood of P, I can say, and that's the parameter. Okay? That means this is the line T is definitely a tangent line because it's touching. And another important thing in calculus means touching means like we'll have the same direction. Okay? The tangent line must have the same direction as the curve at the point of contact, the point of the tangency. Okay? And you can even see, if I will zoom in, if I will go extremely close to that point, the point P, the tangent line and the curve, we don't even see the difference. We can't distinguish the difference. They are almost the same. That means that's the idea. Have the same, like the same slope, the same direction of the line and the curve. And then we can call the line tangent line. Okay. That means I believe we understand the definition of the tangent line. And then let's see, I do have a first example for us, that we have to find an equation of the tangent line to the parabola x squared at the point 1, 1. And I draw the parabola for you. Everybody knows the parabola, x squared. Okay. And the point 1, 1, and this is tangent line. That means since the point is given, I like to start with the point slope form of the line because it's just the equation of the line. Of course, it's the special line, is the tangent line, but it's still a line. That means if you remember point slope, which probably I will use a lot, point slope, because point is given, we do have still a question mark slope. Okay? That means how can we find that slope? I can definitely substitute point. Okay, that means I will have y minus 1 and then slope x minus 1, because this is 1, 1. But I still need that slope. And we remember the definition of the slope, rise over run, which means the changes along the y and changes along the x, the ratio, the quotient, delta y, delta x. But in order to get the changes, I need at least 2 points, because I have to find, let's say y2 minus y1, x sub 2, x sub 1. But I don't have it. That means how can I find a slope between point and itself? Yeah, I will have 1 minus 1, 1 minus 1, 0 over 0. That's a little bit weird at the moment. Okay? That we can see that's the thing. We're trying to find, because that's the rate. We know that the slope is like a rate of change. The rate of change in y's over the rate of change in y's and x. Okay? That we can see that's the problem. That's what do you think? What do you think? How can we approach this at the moment? Like how can I find it? Maybe I can approximate. Like how? Like what should we do in order to find, to approximate, to estimate the slope of the tangent line? Yes, thank you, Zach. That's a really good idea. That means Zach is using, everybody can see the chat box, I'm assuming. And Zach actually is using another terminology, secant line. Okay? That means secant line, it's definitely the line that is intersecting the curve twice. That means we will have 2 points. And Zach is suggesting that we can use the slope of the secant line. Perfect. Then we will have 2 points. Let's see, and I think I did this. Let me, okay, I can have this for now. That means that's my original point 1, 1, okay? And then I pick another point, x. That means I pick, this is 1, this is x, the corresponding value for 1 is 1, and the corresponding value for x, of course, is x squared, okay? That we can see. And then I connect these 2 points, blue line, secant line. Easy to find a secant. But instead of x and x squared, I think I pick 2. Oh yeah, let's use that slide. Again, 1, 1, and then 2 corresponding value is 2 squared 4. Okay? And now, slope is, of course, rise over run, our beautiful algebra definition. This is my rise, this is my run. Okay? And then the value for Q, the Y value is 4. For the point P, I cover P, it's 1, 4 minus 1, which we can even see. This is the difference in these values, 4 minus 1, 2 minus 1. Okay? And then we have 3 over 1, 3. Okay? That means this is okay. That's the slope, okay, of the secant line. It's still not our tangent line. And what do you think? It's a good approximation? Can I say that tangent line has the slope 3? Of course, this slope is for the blue line, okay, for the secant line. It's at least something, right? But what do you think? Is good or not really like accurate? And what we can do? Okay, Eric, yes, okay, of course, it's not close enough. It's a little bit, yes, the tangent line, we can see it's less steep. That means will be slightly smaller, correct? That means, what do you think? What was my, I can say, mistake or not a good choice that I did? How can we improve this? Yeah, it's not, yeah, you said that it's not close enough, Zach. That means I like it. That means this. Because what I did, I choose the point 2. Okay? Theoretically, it's close to 1, but actually, practically, we do have more points, or I would say infinitely many points that are much, much closer to 1. Because it's enough to pick 2 points, and 2, I can say it's very far away from 1. Okay? That means this point to the point Q that I picked, it's not a good choice. Of course, I did for purpose, we did the slope, but what I can do, I can move the point Q really close. I supposed to be extremely close at 1. That means, let's say, not 0, 1.000001, for example. Yeah? And then I can compute the slope, and I believe if I will compute the slope of that secant line, I will have almost the value of the slope of the tangent line, because this is, we can see, extremely close. Okay, that means, let's see. That means that's the idea, to move. This is a little bit different, but this is my point 1. Let's say this is my original 2 that I picked, but I really have to move closer, or even closer, because I pick, let's say, 1.01 for now. That means I definitely have to move. That means point Q, okay, in order to get the tangent line, the point Q, the x coordinate must approach 1. It's not going to be equal to 1, never, but it will be extremely close to 1. And that's what I was telling you on the previous slide, 1.000001. Okay? That means that's the idea. The x coordinate, I can write the other way, the x coordinate of the point Q will approach 1. that we can see I can't say it's equal to 1. No. Yeah, this is for the point Q, but it's approaching 1. It's getting extremely close. That's the X. Okay. And let's see what I have. I did use, of course, the calculator. We know that we're not allowed to use the calculator in this class, but this is just from the teaching purpose. On the test, we will never ask you a question that requires a calculator. All of the numbers will be nice and friendly. Okay, that means let's see what I did. I took a few values for the point Q, and I did calculate the slope. That means the first one, this is 1, and first one I picked 1.5. That means the corresponding value for 1.5 is 225. The corresponding value for 1 is 1. And then I have the difference in y's, difference in x. The slope is 2.5. Now I'm getting closer. This is 1, and this is 1.1. Of course, I don't want to write so close, but we can see this. The corresponding value is 1.1 squared, which is 1.21. The corresponding value is 1. And then difference in y's, difference in x. The slope of this line is 2.1. And then I actually move the point Q really close, 1.01. That's the corresponding value, and that's the slope. That's what do you think? 2.5, 2.1, 2.01. How can we approximate? What do you think? What will be the slope of the tangent line if I will get even closer? 2.5, 2.1, 2.01. Don't be afraid. Yes, right, roughly 2. And actually, I kind of did this approximation too. If the point Q will be almost 1. But I can't put 1, because 1 minus 1 in the denominator will give me 0. I can't divide by 0. Okay, that we can see almost 1, which means the slope will be almost 2. Okay, good guess, Eric. And what I also did, I did this on the left-hand side. You can see this is on the right-hand side. We can also try to check. Let's look at this. This is my point 1, and this will be point Q, 0.5. And the same idea. The slope of the blue line, following the formulas, and I've got 1.5. And then having my point 1 and point Q is 0.9. Doesn't look on the picture, but I'm getting closer in my calculation. The slope is 1.9. And I've got even closer. This is 1, and this is 0.99. Okay? And the slope is 1.99. And of course, we're assuming that the slope will definitely be 2. If I will get even closer, 0.99999. Okay? That we can see what's happened. We can still estimate, right, slope of the tangent, but please remember the point Q, the second point, will be never the point of contact, never the point of the tangency. Yeah? We always, that means theoretically in this calculation, we're calculating the slope of the secant line on the teeny tiny interval, x interval. Okay, that means now let's put some general notations. That's what we have. The slope of the tangent line, it's like the limiting position of the slope of the secant line. That means, again, the word limit, the limit of the slope of the secant line. Because we can see the secant, the other point, it's getting closer and closer and closer to the point P, but we do have that limit. Right? That means we will use the symbols, limit, yeah? And I will not type the whole word, I will just type LIM, limit of, and that's the secant line, the slope of the secant line PQ, and always, because we will, of course, we will use a lot limit notation, please remember, underneath the limit, we always have to indicate what limiting position we took place. That we can see the point Q, it's approaching point P. Okay, and this is tangent line. Slope, of course. Slope of the tangent. Slope of. Okay, now let's look at this. This is more mathematical. Yeah, this is just the description. That's one more time the same thing. Limit, and x is the x coordinate of the q, and 1, of course, is the x coordinate of the point P. That means x is approaching 1. That was that's what took place. And this is just the formula of the slope of the secant line. The x value minus 1, and that's the y values, because the function is defined as a x squared. I can even say 1 squared. X squared minus 1 squared, x minus 1. Yeah, that means this is simply the y values and the x values. And we know that it's equal to 2. Normally, I can say that we did the approximation, okay? That means I should maybe have this symbol, but we have to remember that we will always put equal sign, because this approximation will be kind of like hidden behind the limit idea. That means, as if we understand what limit means, we can simply say the limit is equal to 2. We know it's not exactly 2, it's approaching 2, like 2.00001 on the right hand side and 1.99999 on the left hand side, but that's behind that word. We perfectly fine to put the equal sign. Okay, that means the slope is 2. Yeah, but that's the notation. I mean, probably this is the first time that you see the limit idea based on the tangent line. Okay, let's see. And this is the equation of the tangent line. I did finish my point slope form. Let me remember, that's point, that's slope, and I can distribute 2x minus 2, and I can add 1 to both sides. And just a little bit of algebra. Okay, but the main thing was finding a slope of the tangent line. And please remember this. Okay, slope of the tangent line is simply a limit of the slope of the secant line. And that's the nice notation. Okay, now let's look at the same thing, but from one of the application perspective, velocity, speed, velocity. Okay, that means what we will try to do. Okay, we can try to read this, but I can explain. We are okay to compute the average rate of change. Yeah? The same thing, because the average will give me 2 points of the time. I can find the distance. I can find the initial time, the terminal time, and that's not a problem. Distance, changes in distance, changes in time. Yes, that's my distance. I can say maybe d, and that's the speed. Okay, that's not a problem. But now we have to think, yes, what is the rate of change, the speed, the velocity at one single point? Yeah? That means you can probably imagine that you starting your trip, let's say at 1 p.m. and you finish at 4 p.m. Okay? And let's say you drove 150 miles. I have the graph on the other side, but let's see. That means, can you tell me, if you were driving from 1 p.m. to 4 p.m., 100 miles, what is your speed? Can you tell me the speed? The velocity is more scientific. Oh, distance over the time? No, you can give me, Carl, thank you. The distance was 105 miles, and time, of course, was 3 hours. Yes, thank you, 50, thank you very much. 50 miles per hour. Thank you, Regina. That's what I said. Everybody can compute this. But now you can think that you're driving, I don't know, if it's like maybe from from the University Park to Pittsburgh, or maybe to Pittsburgh is close, to Philadelphia, maybe that's 3 hours. I don't know exactly the distance, but okay. But then what you can imagine that you're driving, and at some point, somebody took the picture of you, okay, like at one point, yeah, and if you look at the picture, you will probably say, oh, it's static, you're not moving, right? But you know that you're actually driving. That means we are interested. The question is, what is your speed at that moment? Like, let's say exactly at 2 p.m. What was your speed? Okay. That means we can probably say 0, but of course we know that it's not a realistic answer because it's not really 0. And I'm saying 0 because exactly at 2 p.m. we can theoretically say that you're not moving. Yeah, like taking this picture. On the picture you will be not. It's like just at 2 p.m. you're exactly at one point, but you're still driving, and we still want that speed. And when you will probably check your speedometer, it will show you the speed, maybe 50, maybe 55, because of course 50 is the average. You could drive sometimes slower, sometimes faster. Okay. Of course 50 it's a little bit too slow, but it's still okay. That means maybe you're driving exactly 50, maybe 55. That means how do we know? Yeah. That we can see it's to find the instantaneous rate of change, instantaneous velocity. It's similar problem to the tangent line, because what I need the distance. That will probably I will take the time interval. I will take like from 2 p.m. until like 2 and 1 second. Oh, okay. Let's say 0.01 hour. Okay, which will be, we have 60. Yeah, it's okay. I can, that we can see I have to, like, let's say 2 hours and 1 second, like 1 second. It's of course 2 p.m. 2:01. Okay, I can say 2:01 because I don't want to go for the fraction and the minutes and the seconds. Okay, that we can see what we have to do. We have to take extremely tiny time interval, because from 2 p.m. to 2 and 1 second p.m. you definitely moved. That's when we will have a distance that you moved. Probably it's small, extremely small. That means we will probably have the 0 miles, almost 0 miles, and almost 0 seconds. Or I can say 0.00001 mile and 0.00001 second. Okay, that's when we can definitely find. But what is my point? My point is that it's almost the same idea, like a tangent line. And let's look at this. I do have a graph. I just pick a function. Let's say this function represents this kind of like a parabola, quadratic function, which is defined as a 10 t squared, and this represents the position, the distance. Okay, s is the distance, and t is time. And actually it's the same thing, 1 and in hours. 1 hour and from 1 hour to 4 hours. That means I can pick 1 p.m. to 4 p.m. Okay. That means you driving, that's what we're looking for. From 1 to 4, and after 1 hour you drove 10 miles, this is in miles, and after 4 hours 160. It means almost the same scenario. Oh, hang on, I want this. Okay, that means you can definitely tell me the same. The average speed will be 160 minus 10 and 4 minus 1. 150 miles is the difference, and 3 hours, miles per hour. The same idea. Right? Okay. That means no problem. The average velocity, it's simply the same idea like a slope of the secant line, because we have 2 points at the time, and we can compute the changes in values y and changes in values x, which is time and distance in this time. Okay? But now what we would like to do, we would like to find the speed exactly at 1 p.m. Yeah, now it's just 1 p.m. We know that I drove 10 miles at 1 p.m., but this is not really helping me. Right? That's what I said. We have to pick the point that is extremely close, which we will create the same situation like for the tangent line. Instantaneous velocity is the same idea like the slope of the tangent line. Right? That means instantaneous rate of change. Overall velocity, we can say rate of change. That means all of the boxes that you saw in this presentation are important concepts. Okay? The slope of the tangent line will always represent the instantaneous rate of change. In this case, instantaneous velocity. And I can try, we can try to compute, or maybe it's too complicated because we do have a function. Right? That means I can say that this is point x, and this will be actually t, right? T, because it's t, and the value will be 10 times t squared. And slope of the tangent line, of course, is the instantaneous, but we know that it will be limit as t is getting really close to 1, okay? And then I need changes in, I need this distance, and I need changes in time. I need this distance, okay? Rise over run. It means limiting position of the point t, which we know t goes extremely close to the 1 p.m., extremely close, not at 1. And then changes in the top value minus the bottom one, t minus 1. But we will not try, because I didn't use, we have to use the calculator. We have to get the point close to 1, like 1.01, 1.001, or maybe on the other side too. The same like I did for the tangent. But we at least know how to define this. Okay. And I do have, this is actually the end of section 1.4. I do have these 2 exercises, okay? And we can possibly solve one of them, and you can pause the video and solve the other one, okay? And I will add the solution. But we can try which one? Let's do the first one. Draw a graph of a function f of x where the instantaneous velocity at 2 is very different from the average velocity between 2 and 5. Please notice that if we're talking about the instantaneous rate of change, only one point is important. Yeah? That's the whole idea of calculus, is the changes at one point. Yeah? It's the game, like we always defining the rate of change exactly at one point. If the average velocity, average rate of change is involved, we always need 2 points. Okay, let's try to draw something. I can actually t and let's say y. Okay, that means we remember instantaneous velocity, it's exactly the same like the slope of the tangent line. Average velocity, slope of the secant line. So I can draw a function, actually I can draw any function, okay, let's say something like that, and I can pick the point maybe 2, I can pick here, and indicating instantaneous velocity at 2, I have to draw just the tangent. Do you know what's the slope of the horizontal lines? Because actually, accidentally, I got the horizontal line. What's the slope of the horizontal line? It's 0. That means I can say this instantaneous actually rate velocity is 0 at 2. And now what I have to do, I have to have very different average velocity. That means the average velocity between 2 and 5, I mean just different. I don't have to be very different. Okay, I can maybe pick the 0.5 here, and Average means that I have to connect point 2 and 5. 2 and 5. And this is, do you think you can approximate that slope? Assuming that this is the straight line. We just roughly, it's positive or negative? No, it's definitely negative, like maybe negative half, negative 1, doesn't matter. I just want to show that it's different. Okay, that we can see. Average velocity is the slope of the secant line between 2 points. Instantaneous velocity, slope of the tangent line. And please remember, because we will probably in chapter 1, we will slightly touch this concept, but this concept you will have through the entire chapter 2 and 3. And you will ask me, oh, how do you know that it's positive or negative? And I will always tell you, slope of the secant, slope of the tangent. Depends what we're looking for. Okay, and you can try to draw this one later, okay? And I will add the solution. And I do have, okay, one more question, wrapping up the section. Use the sketch of the function f of x, this should be f, below to find the sum, okay, that's why I'm making some exercise, of instantaneous rate of change at 7 and average rate of change on the interval from 0 to 2. That means, first of all, blue. Can you tell me what is the instantaneous rate of change at 7? Can you tell me that value? Look at the graph and tell me the value. 0. Thank you. This number is 0 because I have to find the corresponding value for 7 and draw a tangent line. Oh, and this slope is 0. It's simply tangent line at 7. 0. Okay, now who can tell me the average rate of change between 0 and 2? Who can tell me this value? We have to just find the slope of the secant line. Secant line. Or we do have the answer from Zach, -2. I think it's -2 because that's 0. This is the corresponding point for 0. This is the corresponding value for 2. And I'm just connecting. That means I believe this slope, I wanted to put -2 because we do have 4/2. Yeah. That means the sum, because we would like to find the sum, 0 plus -2, of course, is -2. I can write the final answer for you. And they ask for the sum. But my point again is 0 and -2. Slope of the secant line, average, slope of the tangent line, instantaneous rate of change. And if you understand this concept, I believe the whole chapter 2 and 3 will be much, much easier for you. Okay, I know that I took 45 minutes, but don't worry. I really, even if this section is relatively close, it's extremely important, yes, for the good start. Okay, that's what we will have now. The next section that we have to cover, it's 1.5, of course, the next one, and it's the limit of the function. That's what I just said. The whole idea about the average rate of change and instantaneous rate of change, we will start chapter 2 with that idea. For chapter 1, we will only focus on the limit concept, okay? Because the entire chapter 1 is about the limit, which is also the main, the fundamental of calculus. Okay, that means for now we will not talk about the rate of change, instantaneous and and average at the moment, but just the limit. We will just pull out from the section 1.4 the limit concept. And we will focus on the curves, on the function. That means the limit of the function. That's the point of chapter 1. And let's see, because we also understood the limit idea. Yeah. Like I can even remind you, do you remember that the coordinate x was getting really close to 0.1? Okay, like we know it's not equal to 1, but it's extremely close to 1. That means that's the idea that we're taking. And let's see. The intuitive definition of the limit, because we will not talk about the precise definition. It's a little bit too complicated. The intuitive definition of the limit will tell me like just what we said. We're getting close enough, we approximating, we estimating something, kind of like a rough calculation. You even use the same terminology in the chat when you answer my questions. Guess, of course, kind of educated guess, right? And I have this. That means the limit of the function. This was the picture from algebra. Yeah? Just exactly the value. No problem. I can take the value c, substitute to the formula, and get the corresponding height. But now we have to check like how this the function, like I can maybe write how function is behaving close to the point C, not exactly at the point C, but extremely close. Like what is this level? Yeah, we still kind of looking at that value, which you can probably tell me that is the same. Yeah, that's easy to find. This one is a little bit more complicated, okay? But that's what we will do. We will try to like get close enough, yes, and has the good estimation of the height of the function near to the point C, which we will call that we're looking at the limit of the function f of x as x values, that's the x values, on both sides, they approaches C from the right-hand side and the left-hand side. And we have to find out, as x is getting close to C, what is happening with the function, with the curve. Okay, let's look at this. Oh, okay, I can show you the, the entire screen. That's what I took the same function that I took in the previous section, x squared, and that's the function x squared, just parabola, and we have to investigate how the function behaves close to the point 3. That means this is 3. Right? And you can probably tell me this is the exact value. Can you tell me the exact value at 3? What is the value of the function at 3? Of course, it's 9. It's 9. I mean, it's the 3 squared. It's 9. Of course, that means this is 9. But now, what we're looking for, we will try to imagine that 3 is not there. Okay, like let me put the 9 theoretically is not there. The point on it, like exactly at 3, it's not there. And x is getting really, really close to 3. And we have to find out what's going on with the function, how that curve behaves. I can use the red color for the curve. Okay, that means how the red color is approaching the blue dot, right? But let's see what happened. That means let's look at the points on the right-hand side. 3.1, 3.01, 3.0001. I think I said too many zeros. Okay, and now if I square the values, I have 9.61, then I have 9.0601, 9.006. That we can see, as soon as I'm getting really, really close to 3, the values, I believe, are getting close to 9. Right? We can see that arrow. It's getting really, really, really close to 9, but not at 9. Okay, that means this is just the approximation. And the same thing from the left-hand side. 2.9, 2.999, 2.999, and that's the corresponding values. 8.4, 8.94, 8.99. I think I can also say that from this side, we also approaching 9. That's the numerical proof. That's the graphical proof. You can see the red arrows are approach. You can even see I did point the blue dot. The blue dot is the exact value, which I can use this. Okay. But what I did, I said that the function is also approaching, of course, the level. The level is the same. We can see the horizontal line, if I will draw, it's the same. Okay. That means we can see it's basically easy, but what I would like to stress out, to point out, you can see the blue 9 and you can see the red 9. And theoretically, based on the definition, they are not the same. Of course, you can probably tell me that I'm crazy, like, oh, this is 9 and this is 9. And yes, it is. But if we would like to understand the idea of the limit, yes, this 9 is not exactly the same like this 9, because of course, the blue line corresponds exactly to the blue, okay, let's say the blue corresponds exactly to the value. Oh, I think I changed the colors. Okay, let me do the blue for you. Because I want, that means if x is exactly 3, okay, we have the corresponding value 9. But if x is really, really close to 3, we are really, really close to 9. That means this means that we approaching 9, and the value means that we exactly at 9. I do have this situation again. That means this is the notation, limit of the function f of x as x approaches 3, it's equal to, and we don't know, and of course we get from the table 9. That means this is the original red 9 from the other slide. And do you remember, we're not saying it's almost, like we're not saying approximating, we're not approximating because behind the limit definition, the approximation is hidden, okay? And then we do have exactly the value, which is 9. Yeah? That means my point is for you to remember that this 9 is not exactly the same like this one, but it is 9. That means the exact point will be always the exact point. We are here. But when we're talking about, again, the exact point is just this. No problem. But when we're talking about the limit, we're not at 3. We're really close to 3 on both sides. And function is approaching what level? Of course, 9. That means, please remember, we never, even if the point is not in the domain, we can still get the limit. Okay, that means that's the limit concept. And I do have some description one more time. Oh, I think for all of the students that you never had calculus, we will say this way, that we will express the limit of the function f of x, like that, limit of f of x, as x approaches 3, it's equal to 9. Okay, and the general notation, limit of the function f of x, as x approaches any value, a, the value that we pick, it's equal to L. And then we do have like another description. You can pause the video and you can read this description. We can see the value of the function f of x tends to get closer and closer to number L as x gets closer and closer to the x value a. Okay? On both sides, of course. Or we can have another. Also, please note that we can compute the limit even if the number a is not in the domain of the function. We may have an empty open dot, empty dot, and still find, approximate the behavior of the function. And I know that I'm running out, but this will be the last slide, okay? Because I would like you to help me with the question. That means find the limit of the following 3 functions as x approaches a. And we can see this is a, A and A. This is just the continuous function. Domain are all of the real numbers. That's R. All of the real numbers. For this one, for the second one, we have similar function, but we can see that's the open dot and the value is somewhere else. That means, again, we have some type of discontinuity, but all of the numbers are in the domain. The last function doesn't have the value at A. That means domain is all of the numbers, but not A. Yeah, we don't have them. We can see it's open dot only. Okay, and what I like you to give me, the limit of the first function. What is the limit of the function as x approaches A? Do you think you can tell me? This is the L. Who can tell me? Of course, you saw the number. Yeah, I just need, for each of them, A, B, and C, I would like you to tell me limit and the exact value. Limit and the exact value. And we will be done. Okay, that's me. What is the limit as x approaches A? No, you can probably tell me. We're not exactly at A. That's we're getting really, really close to A. The x values are getting close and close. And we're trying to find out how function behaves. And we can see the function is approaching that dot. I should maybe keep the O. I mean, we still have the dot, but doesn't matter. We're not exactly looking at the dot. We're looking like how function behaves. And function is approaching that level. Of course, L. Thank you, Zach. Right? That means the limit. I don't want to mess up. Limit is L. And what about the value? Value is the exact dot. That means if we have A, the corresponding value, of course, is L. Okay, if you, because we have a little bit different, like all of the functions look a little bit different, and I really want you to understand, okay, understand all of these answers. Okay, what about the second, B? What is the limit as x approaches A of the function f of x? How function f of x behaves really, really close to A? We can see now we have open dot and we have the value at the level M. Can you answer that question for me? You can use the chat box. Of course, I can tell you, but that's... everybody, can everybody try? Zach said is L again. Eric said L. Okay, a few more. I know it's... Nobody can see you. Gabby said L. Okay, Tyler said L. Okay, thank you. I think it's L. Because we can see, we're not looking, do you remember, we're not looking exactly at this for now, we're looking how function behaves. As x is getting closer to A, the value, I mean the behavior of the curve, the function, it's still approaching L. Of course, it's still approaching that level, L. And now, what is the value of the function at A? Exactly the value. I'm looking for the solid dot, right? That means the value is actually M in this case, okay? And now the last one. What is the limit of the last function as x gets really, really close to A? How the curve behaves? It's again L. We can see the function, because if you will notice, function, the curve, has the same shape. That's the curve, and the third one. That means the function does the same thing, L, L, and L. Doesn't really matter if we have a dot, or we have dot somewhere else, or if we don't have the dot at all, the point, it's still the same shape of the function. At close to A, always is the level L. And for the last one, we can see we do have an open dot, and we don't have this. I will use for values does not exist, DNE. That means the exact value, the exact dot doesn't exist. We can see we have open dot. Okay, I still have a few things, but as I said, I will finish on my own, and please check for the additional video. But what I would like from you, of course, the section 1.4, the instantaneous rate of change and the average rate of change, slope of the tangent, slope of the secant, respectively. That's section 1.4. And the limit idea, the behavior of the function, the limit idea for the section 1.5. And what we have a big section 1.6, but 1.6 is focused on calculation. That means I will solve lots of limits for you. Please watch the video. If you need some help, you can post the question on discussion board, or you can email me. Okay? Or you can request the office hours, and I can meet with you and explain things. Actually, I can switch the camera. I'm still there. Okay, let's finish, as I promised, just 60 minutes, and the rest of the stuff will be for you on Canvas to watch. Okay? Okay, thank you very much, and thank you for joining me. Okay? And the next session, of course, will be next week, Tuesday, 9 a.m. Okay? Thank you.